I have a shape to show you. You can hold it in your hands, you can fill it with paint, but you can never paint its surface, not with all the paint in the universe. There is no mathematical trick here, and it's a precise mathematical calculation. This shape has a finite volume, but an infinite surface area. It seems to contradict common sense, and it feels like mathematics itself must be wrong. It has even a name worthy of its strangeness. It's called Gabriel's horn, named after the angel whose trumpet call announced the end of the world. And today we are going to calculate exactly why it works. In 1641, the Italian mathematician Evangelista Torricelli was studying a simple curve, the hyperbola, which is y equal 1 over x. He took the portion from x equal 1, stretching to infinity to the right. It rotated the shape, the curve, around the x-axis. The result is a shape like an infinitely long trumpet, and Torricelli calculated two things, the volume and its surface area. And the results, they were shocking. Check the radius of the disk at x equal 1. The radius is 1, at x equal 2, the radius is 1/2, and so on. So to find the volume of this shape, we use the disk method. Slice the horn into infinitely thin circular disk perpendicular to the x-axis. Each disk at the position x has a radius of r equal 1 over x. We pick a portion, and around the center we see the volume of one infinitesimal thin disk, and the total volume is calculated by this given formula, which is nothing but almost pi r squared along the dx. And the volume calculated from here after a simple integration is nothing but pi cubic units. So the volume of this shape is finite. The surface area of a solid of revolution use a different formula. Instead of disks, we use thin bands. Each band is a slice of cone wrapped around the surface. Since y equal 1 over x, we know what is the dy over x, and we have minus 1 over x squared, and this is exactly what we needed to calculate the ds. So let's look at the final form of the integral. We have this square root, which is larger than 1 for all the x values. So we can use a lower bound, and what we obtain is, after this integration, you have 2 pi ln of x, and you have to integrate from these boundaries. So you have the surface area of this shape larger than infinity, which means it is infinite. The critical difference between the volume and the surface area is r versus r squared. And what we mean by this is the following. As we see from the integral, the volume integrates over pi r squared. So the volume integrates over pi r squared, which is pi over x squared dx. And this converges because the integral of 1 over x squared converges. And the surface integrates over 2 pi r ds. Once you do the integration, what you see is there is the integral of 1 over x dx, which is divergent. The horn narrows, but not fast enough for the surface to be finite. Here, if you calculate, what you get for the volume is pi, and what you get for the surface area, it's infinite. You could fill Gabriel's horn with exactly pi cubic units of paint. But if you try to paint the surface, all the paint in the universe, however thin we make the layer of the paint, would not be enough to coat the horn. So Gabriel's horn is a lesson about where the intuition fails, and our intuition says that an infinitely long object must have an infinite volume, but it's wrong, it's finite. Then our intuition says, well, if the volume is finite, the surface area must be finite too, but it's wrong again because it's infinite. So mathematics never stops surprising us, regardless of if we are talking about angel's horn or what's inside of black holes. What a great compass mathematics is against our common sense. And if this ignites your curiosity, subscribe to Breaking Space Time, and I'll see you in the next one.